While following the talks of this morning, I realized that not everyone might even know what my title means. So let me first introduce every word of my title. So I will be doing time evolution with matrix product operators. So as we have already seen today, there is such a thing as matrix product states, which is a factorized way of writing down array in Hilbert space. And a matrix product operator operates on such a state. And we also write it down as a factorized way. So it's also a product of local finite amount of numbers. And I will be doing time evolution. More specifically, I will be trying to approximate the time evolution operator. What is a time evolution operator? It is the operator that I apply to my state at some time t0, and it gives me the state at a later time. So time evolution right here with matrix product operators right here. So let me formulate the problem. I want to integrate the Schrödinger equation. So given the Hamiltonian for a 1D quantum lattice model, so a Hamiltonian defined on a Hilbert space, which is a tensor product of local Hilbert spaces, what is this time evolution operator? And when the Hamiltonian is independent of time, so it's constant throughout time, we know that it's the exponential function. That will be part one of this talk. And then when the Hamiltonian has a time dependence, it actually doesn't have a closed form anymore. So we will have to resort to series expansions, namely the Dyson series or the Magnus expansion. And I want to be formulated as an MPO to be used in matrix product states. So what is the big deal here? Why is it hard to write down the exponential of a Hamiltonian? So even if I have a Hamiltonian that is written in this nice factorized way with a small amount of numbers, if I want to take the exponential, I will actually, again, make this a dense tensor on the full Hilbert space. So with 2 to the n, with n very large amount of numbers, which is unfeasible to use. So we want to have this in a nice local factorized way. There is a very important language that I will use to construct these MPOs, which is the language of finite state machines. And what I want you all to realize is that Hamiltonians on these quantum lattice systems are sums of mostly trivial terms. So these terms are some small local terms, for example, this D, which acts on one side. And in front of it, it's just all identities, and behind it is also all identities. Same with the term on the top. It's some L, the left of the start of some term, A, the middle, or on the right, but before and after it's just all ones. So it's a sum of mostly trivial terms. And it turns out that finite state machines are the perfect tool to encode this kind of structure. So if you have a sum of local words or local terms, you can represent it as a finite state machine. So what is this finite state machine? It has different states. We start at state 1. State 1 encodes that a term in this Hamiltonian hasn't started yet. We can take any of the transitions along these edges of this finite state machine. For example, just loop back to 1, which means I will just place an identity on my lattice, move on to the next side. I can transition to state 2, which encodes that the term is in progress, thereby placing an L, starting a term in my Hamiltonian. I then can transition to state 3, placing an R, then state 3 encodes that the term has finished. And then when I end up at 3, the only thing I can do is keep placing these identities until the end of my chain. So one term of the Hamiltonian is one particular path throughout this finite state machine. And the Hamiltonian is a sum over every single path in this finite state machine. Now, what is the big deal of these finite state machines? Well, it turns out that the MPO representation of my Hamiltonian is the adjacency matrix of this finite state machine. So this tensor, I have now written as a matrix, but it has 4 legs. That's a bit confusing. So this tensor is viewed as a matrix from its virtual indices. This red and this blue leg is this matrix, and it's the adjacency matrix of this finite state machine. And these empties are then tensor like matrices. And the sum over all paths in this finite state machine is exactly the contraction over these virtual indices. So when I place this Hamiltonian in my network, I will ensure that I start at level 1. So I just put the boundary vector there at 1. And then this contraction over all these different indices is the sum over all paths. Okay, so now we know how to write down Hamiltonians as MPOs, and we know that this is associated with this language of finite state machines. So let's look at part one. How can I encode time evolution for time-independent Hamiltonians? And it turns out that there is a smart way to do this with Taylor MPOs. So if you write the exponential as a Taylor series, the question is, how can we craft a smart encoding, so an encoding that has a finite amount of numbers of this object? And an all-star team of researchers from Ghent, namely Maarten van Damme, Jutta Hageman, Laurens van der Straten, together with Ian McCullough, came up with this Taylor MPOs, which are accurate up to any order. You can choose the order. Of course, if you choose a higher order, the bond dimension will be bigger. And the error scales with the time step you take to the power n. And it works for long-range Hamiltonians and also finite and infinite systems. Okay, so let's look at an interesting and important property of the exponential. So if my Hamiltonian is the sum of local terms, the Taylor series of the exponential is written like this. If I rewrite these sums in a nice way to get rid of these combinatorial factors, you can see that higher order terms, or for example, this second order term, can be written as a product of two lower order terms. So this extensivity of the exponential, we will try to exploit, and this is actually the motivation behind the transformation I'm about to explain. So we want to have some MPOs, some finite state machine, and we want that after we have placed some term, 1 plus tau h, we can keep on adding these terms because they will add up to higher order. They will combine to higher order terms of this Taylor series. So as we have this finite state machine before, as I told you, once you reach 3, you will just keep on placing identities. Well, we will just change the 3 to a 1, so we will reroute the end of a finite state machine to the beginning again. We have finished placing some term. Now we will just place another one. And we will multiply these entries R and V by tau, the time step. And that turns out to actually be an MPO encoding of the Taylor series of the exponential up to first order. And this is already been known since 2015. It was introduced by Michael Vanthilt, and he called it the W1 MPO. And this operator that this thing encodes is the Taylor series of the first order, and all higher order terms that can be made up of this first order. So this is the disconnected product. So the disconnected product of h squared is just any term in h squared that is made up of one term of h and another term of h that do not overlap. So all higher order disconnected terms are included in W1 for free. So what did these researchers from Ghent do? Well, they generalized it to higher orders. So this is slightly bigger finite state machine for h squared. And you just look at, for example, previously we looked at the level 3 and we rerouted it 1. Now we just take the 3 level, 3 1 and the 1 3 level, multiply it by a right factor of tau, reroute it to the first level, and then we get the second order Taylor series. Okay, so this is already known, this is already out. People should start using it. So what happens if your Hamiltonian gains time dependence? Well, as I said, there is no closed form solution to the time evolution operator. We will have to go through the Dyson series or the magnitude expansion. So now in this talk, I will only talk about the Dyson series. And this is a recent paper that I made together with the previous authors, which encodes the Dyson series as an MPO for any order n, which also works for long-range Hamiltonians, finite and infinite systems. Okay, so this resembles the Taylor series we had before. Now we have a bunch of integrals. I will write it in an easy way. It's identity minus, this was previously dth, dt squared h. Now these are integrals. This is fi is this integral over one function, driving function. This is a time-ordered integral over two functions. So before we have these different orders of the time step, now we have these time steps, these small parameters that depend on every term of the Hamiltonian. So we will need to, if we want to do an operation or a finite state machine, we will have to insert these integrals at the right places instead of just putting dt squared at every second order term. So if you look at a Hamiltonian with two driving functions, so we have two separate Hamiltonians. This is the image that we had before. This is just a Hamiltonian with two different driving functions. We will have to find a way to associate the integral over f1 with this branch and the integral over f2 with that branch. To that end, we introduce a little trick. We do not have one tree level, but we have a tree level for every single function, a driving function Hamiltonian. And now we will just reroute this back to 1, as we did before, but now times the integral over f2. Same with the top branch. Then you can ask the question, before we could easily see that lower order terms add up to higher order terms. Is this again the case? And well, yes, it is, because of this identity of the time ordered integrals. So the first order Dyson NPO is connected to first order, but it also has all higher order disconnected terms. So we tested this with respect to state-of-the-art methods, namely TDVP, which is this gray line. This is the time step that we take. This is some integration of some propagation of some initial states under a time-dependent Hamiltonian up to some final time. And this is the error at the end, so the fidelity with some reference state. And as you can see, these different orders of the Dyson series actually have different slopes, so they correspond to integration schemes that have different scalings of the error with respect to the time step. We clearly beat TDP, which is the only thing that was out there for time-dependent Hamiltonians. And what you can actually see is that these lines are nice and straight, except this third and fourth order term. These third and fourth orders have this plateau at around the level of 10 to the minus 5, 6. And that's actually because we're comparing to TDP with a time step of 10 to the minus 6. So with a Dyson NPO of order 4 and a time step of 10 to the minus 1, we outperform what is out there by taking 1,000,000 steps. So we take 10 steps, which doesn't take that long. TDP takes 1,000,000 steps, and we even outperform that. So I can make this plot, but comparing to my best fourth order Dyson NPO, and then these lines keep on going. But that would be, I mean, I needed some ground truth. I cannot just compare myself to myself. Therefore, there is this plateau. So to recap, I talked to you about time evolution with matrix product states. I encoded the time evolution operator as an NPO. And my recent work makes an NPO encoding of the Dyson series, which is accurate up to any order n, works for long-range interactions, finite systems, and infinite systems, and it outperforms what is already out there. Thank you for your attention.